Welcome to Get Your FRQ On. This question is from 2010. It's question 4, and it is not calculator active. In the question stem, we have a region R bounded between two curves in quadrant 1. And in part A, we are asked to find the area of region R. Now, based on what the graph and the functions are, I think it would be easier to integrate this with respect to y. I think it's just going to be an easier integral to find. You don't have to do this, but it will be a little bit trickier. Not terrible, but I think it's just easier to do it with respect to y. And if we do that, we're going to have to take one of our boundary functions, specifically the boundary function y equals 2 square root x, and rewrite it as a function of y instead of a function of x. So taking y equals 2 root x, dividing by 2 and squaring, we get x equals y squared over 4. And based on the information provided in the question stem, the area of R is just the integral from 0 to 6 of y squared over 4 dy. Right? Now maybe you can see why I'd rather do this in terms of y rather than x. Don't deal with the square root. This is a really easy antiderivative to find. The antiderivative of y squared over 4 is y cubed over 12, so that area of R is just going to be y cubed over 12 evaluated between 6 and 0, which is going to get me 216 over 12, and I don't know if you know this, but that turns out to be 18. If you don't know it and you just leave it as 216 over 12, that is also fine. You could probably write it as 6 cubed over 12, and that would also be okay. In part B of the question, we are asked to write an integral for the volume of when the region R is rotated around the line y equals 7. Notice we need to find an integral for this. We do not need to evaluate it. So one of the things to notice is that the line y equals 7 is above the upper boundary of this region. So if we rotate this region around the line y equals 7, there's going to be a cavity. Basically a giant cylindrical shaped hole that's been bored out from the middle of this solid. All right, so we have to account for that somehow. All right, so what we need to do is we need to find the volume using our big radius. Right? In this case, that radius is going to be from the function 2 square root x. So we need to integrate from 0 to 9, 7 minus 2 root x squared times pi dx. Now that's going to find the volume of the giant solid without the cavity removed. Then I have to remove stuff from the cavity, which would be pi times the integral from 0 to 9 of 7 minus 6 squared dx. This is my small radius. And that can be combined into one integral, pi times the integral from 0 to 9 of 7 minus 2 root x squared minus 1 dx. And since we don't need to evaluate this, I'm not even going to try. In part C of this question, we are told that R is the base of a solid, and for all values of y between 0 and 6, cross-sections taken perpendicular to the y-axis are rectangles, whose height is 3 times the length of the base of that rectangle in the region R. And then we are asked to find an integral for the volume of this solid. Now, since cross-sections are being taken perpendicular to the y-axis, we're going to have to integrate with respect to y. It's actually an easier integral to do that way, so this is fine. All right, but this height, 3 times the base of the rectangle in R, well, the base in R is y squared over 4, and 3 times that would just be 3/4 y squared. So that function gives us our height as a function of the y coordinate. So our volume, we have to integrate from 0 to 6, my height function, h of y, times the base function, which is y squared over 4 dy. That's the integral from 0 to 6 of 3/4 y squared times y squared over 4 dy, which turns out to be the integral from 0 to 6 of 3/16 y to the 4th dy.